the quality of service concept. What is this quality of service concept? Let us begin by giving a scenario. Imagine driving on a heavily congested road and you are in a rush to meet a friend for dinner. You hear the siren and see the lights of an ambulance behind you. You need to move off the road to let the ambulance through. The ambulance getting to the hospital takes priority over you getting to the restaurant on time. Much like the ambulance taking priority in the traffic on the highway, some forms of network traffic needs priority over others. In this scenario, this is just like we need to prioritize some network traffic over the other traffic, just like the ambulance scenario. We need to prioritize, we need to give way to ambulance to save the life of any passenger carried by an ambulance. Just like in network, we need to prioritize important traffic in order to save a bandwidth and give way to the most important traffic that is flowing in the network. That's what quality of service is all about. Now in this chapter, we're going to explain how networking devices implement QoS, or the quality of service. Module 9 include the following subtopics. First off is the network transmission quality. This would explain how network transmission characteristic impacts the quality. Next off is the traffic characteristics. It describes the minimum network requirements for voice, video, and data traffic. Next is the queuing algorithms. It describes the queuing algorithms used by networking devices. And the quality of service models. This describes the different quality of service models. And the last one is the QoS implementation techniques. This explains how quality of service uses mechanisms to ensure transmission quality. Now, for network transmission quality, to meet the quality of the transmission, we need some sort of traffic prioritization. We need to prioritize, as we have mentioned in our introduction. When the volume of traffic is greater than what can be transported over the network or across the network, devices queue or on hold the packets in memory until resources become available to transmit them. Queuing packets causes delay because new packets cannot be transmitted until previous packets have been processed. If the number of packets can be queued continues to increase, the memory within the device fills up and packets are dropped. One quality of service techniques that can help with this problem is to classify data into multiple queues. As you can see in the figure, there is a high quality queue, there is a medium quality queue, and low priority queue. High priority queue, medium priority queue, and low priority queue. A device implements QoS only when it is experiencing some type of congestions. If you notice in the figure also, there are three traffics: the voice over IP traffic, a financial transaction. It is the data traffic and the web page also. This is a data traffic that goes into the router. So we need to apply some sort of prioritizing this traffic. In prioritizing a traffic, we need to consider the following: the bandwidth, congestions, delay, and jitter. Network bandwidth is measured in the number of bits that can be transmitted in a single second, or bits per second, or BPS. For example, a network device may be described as having the capability to perform at 10 gigabit per second, or 10 Gbps. The network congestion causes delay. An interface experiences congestion when it is presented with more traffic than it can handle. Network congestion points are ideal candidates for quality of service mechanisms. As you can see in the figure, these three examples shows three examples of typical congestion points: the aggregation, speed mismatch, and LAN to WAN. Delay or latency refers to the time it takes for a packet to travel from the source to the destination. Two types of delays are fixed and variable. A fixed delay is a specific amount of time a specific process takes, such as how long it takes to place a bit on the transmission media. A variable delay takes an unexpected amount of time and is affected by factors such as how much traffic is being processed. Sources of delays are summarized in the following. The first one is the code delay, where this is the fixed amount of time it takes to compress data at the source before transmitting to the first internetworking device, usually a switch. The second one is the packetization delay. This is the fixed time it takes to encapsulate a packet with all the necessary header information. The third one is queuing delay. This is the variable amount of time a frame or packet waits to be transmitted in the link. And the fourth one is the serialization delay. This is the fixed amount of time it takes to transmit a frame onto the wire. The fifth one is the propagation delay. This is a variable amount of time it takes for the frame to travel between the source and destination. And the last one is the jitter delay. The jitter delay, this is the fixed amount of time it takes to buffer a flow of packets and then send them out in evenly spaced intervals. These are the sources of delays. Jitter is the variation of delay of received packets. At the sending side, packets are sent in a continuous stream with the packets spaced evenly apart. Due to the network congestion, improper queuing, or configuration errors, the delay between each packet can vary instead of remaining constant. Both delay and jitter need to be controlled and minimized to support real-time and interactive traffic. Now, what is this packet loss? Without any quality of service mechanism in place, packets are processed in the order in which they are received. When packets are later converted back into analog or when congestion occurs, network devices such as routers and switches can drop packets. This means that the time-sensitive packets such as real-time video and voice will be dropped with the same frequency as data that is not time-sensitive, such as email and web browsing. When a router receives a real-time protocol or RTP, digital audio stream for voice over IP, it must compensate with the jitter that is encountered. The mechanism that handles this function is play-out delay buffer. This is the mechanism that handles the jitter. The play-out delay buffer must buffer these packets and then play them out in a steady stream, as you can see in the figure. The digital packets are later converted back to an analog audio stream. Play-out delay buffer compensates for jitter. And in the figure, the packet drop due to excessive jitter. The packet loss is very common cause of voice quality problems on an IP network. In a properly designed network, packet loss should be near to zero. And the voice codecs used by the DSP can tolerate some degree of packet loss without dramatic effect on voice quality. Network engineers use QoS mechanism to classify voice packets to zero packet loss. Bandwidth is guaranteed for the voice calls by giving priority to voice traffic over traffic that is not sensitive to delays. And let us move on to the network traffic trends. What are the traffic trends nowadays? In the previous topic, we learned about the network transmission quality. Now in this topic, the transmission quality, we learn about the traffic characteristics such as voice, under the voice, video, and data. In the early 2000s, the predominant types of IP traffic were voice and data. Voice traffic has predictable bandwidth, need, and known packet arrival times. Data traffic is not real-time and has unpredictable bandwidth need. Data traffic can temporarily burst as when a large file is being downloaded. This bursting can consume the entire bandwidth of a link. More recently, video traffic has become the increasingly important to business communications and operations. Consider that organizations now commonly use video conferencing to meet with users and clients. High-definition video surveillance to remotely monitor facilities and equipment. And video conferencing, video streaming for a variety of purposes including training, according to the Cisco Visual Networking Index or VNI. By 2022, video will represent 82% of all the internet traffic. In addition, mobile video traffic will reach 60.9 exabytes per month by 2022. The voice traffic The voice traffic is predictable and smooth and it's very sensitive to delays and drop packets. It makes no sense to retransmit voice if the packets are lost. Therefore, voice packets must receive a higher priority than other types of traffic. And under the voice quality, voice can tolerate a certain amount of latency, jitter, and loss without any noticeable effects. Latency should be no more than 150 milliseconds, and jitter should be no more than 30 milliseconds. And voice packets loss should be no more than 1%. Voice traffic requires at least 30 kbps of bandwidth. And the table shows that the summary of the voice traffic characteristic and requirements. The voice traffic characteristic should be at least the voice should be smooth, benign, drop sensitive, delay sensitive, and UPD priority. And for one-way requirements, latency should be less than 150 milliseconds, and the jitter should be less than 30 milliseconds, and the loss should be less than 1%. And at least the bandwidth is 3228 kbps. That is the voice characteristics. Moving on to the video characteristic. The video without quality of service and a significant amount of extra bandwidth capacity, the video quality typically degrades. The pictures appears blurry, jagged, or in slow motion. The audio portion of the feed may become unsynchronized with the video. In contrast, the number and size of video packets varies every 30 milliseconds based on the content of the video. And the video traffic tends to be unpredictable, inconsistent, and bursty compared to voice traffic. And compared to voice traffic, compared to voice, video is less resilient to loss and has a higher volume of data per packet. And UDP ports, the UDP ports such as 554 are used for the real-time streaming protocol or RSTP and should be given priority over other less delay sensitive network traffic. Similar to voice, video can tolerate a certain amount of latency, jitter, and loss without any noticeable effects. Latency should be no more than 400 milliseconds. Jitter should be no more than 50 milliseconds, and video packet loss should be no more than 1%. Video traffic requires at least 384 kbps of bandwidth. The table gives a summary of video traffic characteristic and requirements. The video traffic characteristics are: number one is bursty, greedy, drop sensitive, delay sensitive, and UPD priority. And the latency in one-way requirements, latency should be less than 20 to 400 milliseconds, and the jitter should be less than 30 to 50 milliseconds. And the loss should be less than 0.1 to 1%. Bandwidth should be at least 384 kbps to 20 mbps. That is for the video. The last one is the data. Most applications use either TCP or UDP. Unlike UDP, TCP performs error recovery Data applications that have no tolerance for data loss, such as email and web pages, use TCP to ensure that if packets are lost in transit, they will be resent. Data traffic can be smooth or bursty. Network control traffic is usually smooth and predictable. When there is a topology change, the network control traffic may burst for a few seconds, but the capacity of today's network can easily handle the increase in network traffic as the network converges. However, some TCP applications can consume a large portion of network capacity. Like the FTP will consume as much bandwidth as it can get when you download a large file, such as movie or game. The table summarizes data traffic characteristics. So you have to consider in the data traffic characteristic, number one, smooth and bursty, benign and greedy, drop sensitive, drop insensitive, delay insensitive, and TCP retransmit. So these are the common characteristics of data. And the factors to consider for data delay, number one factor is it interactive? If that is interactive, if that is a mission critical, prioritize for the lowest delay of all data traffic and strive for 1 to 2 seconds response time. And in a non-mission critical, applications could benefit from lower delay. For non-interactive, mission critical, delay can vary greatly as long as the necessary minimum bandwidth is supplied. And for non-mission critical for non-interactive, gets any leftover bandwidth after all voice, video, and other data applications needs are met. Although data traffic is relatively insensitive to drops and delays compared to voice and video, a network administrator still need to consider the quality of user experience, sometimes referred to as quality of experience or QoE. And there are two main factors that network administrator needs to ask about the flow of data traffic. Does the data come from interactive applications, or is the data mission critical? So those are the important factors that has to be considered in the data traffic. So that ends our part 1 of this topic, the network transmission quality and the traffic characteristics. For the next video, we're going to tackle the queuing algorithm models and implementation techniques.